nice relaxation in regardless of whether you were here or there or
I got the sun's
wherever.
rays.
You got the sun's rays,
Yeah.
little vitamin D in your body. Yeah, it's refreshing. There, I got at least 2 emails from staff members here, like teachers and stuff, saying that we only have 49, 48 days, depending on how you count it, before summer, which seems kind of ridiculous to me. Like, that's less than 50, which I mean, like, duh, yes. But like, I feel like 50 is like a pretty big mark. So anyway, we're almost there. And you guys know this as well as anybody else. After spring break, it just goes fast. So, hold on, do what you need to do. But just, what's that? You think it goes slow? I always feel like it goes fast. Like it just like things just keep happening. And yeah, but if it has gone slow for you in the past, I hope it goes faster for you today or this year. If that's what you want, I suppose. All right. So I'm going to introduce you to some beats quick, and then we're going to do a lab. That'll be our day. So if you're going to take a look at this sheet, the grayish sheet that you have in front of you, you're going to do a couple of these things on your own, and then we will do some things together. So you got 2 waves here. It says that I would like you to determine the frequency of the wave. Okay? So that's the first thing you're going to do, and you can do that with your partner. You can do that by yourself, whichever way you'd rather. And then once you know that, I want you to look at the 2 waves together and imagine those 2 waves are in the same place at the same time. Okay? And then I want you to draw the resultant wave down here below. Okay? And then name that. What is that called? Think you can do it? Do it. Give it a shot. So get your pencil out. Start counting. Remember what frequency means. And it's been a week. So if you need if you need a moment to like review, then get your notes out. We spent a lot of time before break talking about this stuff. If you need a week, then I'm not going to give you a week, but you can, have a moment, have a day. Okay. So go ahead and do what you need to do to figure out the answer to that question. Just do that first one. That sound like a decent plan? All right. So let's talk about this. So the first task that you are charged with in this, it says for each of the waves included, determine the frequency of the wave. So it's been a few days, but I want to make sure that you really understand this, because if you don't, then the lab is going to be hard. The frequency. What does frequency mean? It's measured in hertz. What does frequency mean? Go.
It's the number of vibrations an object makes per second.
Yeah. Number of vibrations or cycles per time, right? All right. So how do we figure out the frequency of this wave, this one up here? So you counted like these guys here? Yeah. So is that a cycle from here to here? So I just want to know. So from blue dot to blue dot, is that a cycle? No. Where does the cycle that starts on the first blue dot end? Here?
Yeah.
No. It starts. It's the next node. There. Yeah.
Okay. So this is just clarification from my part that I may have not misled you, but mislabeled. What do we call this line? Does anybody remember? Starts with an E. That's equilibrium. That's where the whatever it is, the material that's moving, whatever it is, that's where it is when it's at rest. Okay? So from blue dot to blue dot now is one complete cycle. Do we start at equilibrium on this wave though? Where does it start?
Crest.
It starts up here at a crest. So I'm actually going to start counting at the crest. This seems to make sense to me. Where has it gone through one complete cycle then?
Next crest.
The next one. Yeah, right here, right? So that's one. So there's one cycle from red dot to red dot. This would be 2. Count with me. It's more fun that way. So 1, 2.
3, 4, 5, 6, 7, 8, 9, 10.
So 10 cycles, right? 10 cycles that this wave goes through in how many seconds?
2.
2 seconds. So we can either count to 10, which is exciting, or we can just count halfway there, because that's 1 second. Either way, what is the frequency of this wave right here? Hertz. Smart Alec, there you go. All right, so frequency is 5 hertz. How does this one? What's this one? Same. It's also 5 hertz, right? I just want to make sure that we're really aware of that. So we get it. Okay. So bullet point number 1 is done. Number 2 says draw the resultant wave in the space below. So we talked about this on Friday. We talked about interference. Do you remember? If you have 2 things, we can look back at our I don't know if we had it in here, or maybe it was, nope, it was before that even. Yeah, when we have this stuff here, right, where they go up, 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 and this stuff here where it goes down, down, down. I think we wrote that somewhere. I don't remember where it was now. Maybe it was back here. Whoa, it was so long ago. There we go. If you have 2 waves that are both above or below the equilibrium, then what happens to them? What happens to their amplitude? It increases. In fact, it is the sum of the 2 amplitudes. You with me there? Okay, so let's find out what's going to happen in our picture. So here we go. We've got this one right here and this one right here. They're both above the equilibrium point. So what is the amplitude of this wave, the resultant, the net wave going to be from these 2? How do I figure out the amplitude? There's A1. There's A2. We're going to add them together, aren't we? So it's going to be really high. It's going to be like, holy cow, way up here. This distance here is A1 plus A2. Does that make sense? Let's look at the dotted line, just the dotted line points to start, just to make our lives a little bit easier. What about this point way down here? And this point way down here? What are we going to do with those 2 amplitudes? I don't know why we're whispering. So is it going to be up here? Where's it going to be? Way down, right? It's going to be down low. It's going to be way down here, right? This distance is A1 plus A2 as well. Is that making sense? Okay. And then if we go over here, it's going to be up here again, and then down here, and then up here. And then it's going to happen the same way in between. So we're going to have, if we kind of dotted line it, I want you to draw this. Don't just wait for me to do it. Okay. I want you to do it. It's going to go low, and then it's going to go equilibrium, and then it's going to go high, and then it's going to go equilibrium, and then it's going to go low, then it's going to go equilibrium, then high, equilibrium, and then we could connect those dots and make this really tall wave. Whoa! Everybody's going to take note of this because this was like the best time I've ever done that in my entire life. Just going to say. You don't have to draw all of it, but you can draw just that much, and that's fine. The point of this is that the amplitude gets really, really big. Yeah? What kind of interference are we going to call that? Constructive. That's what we're talking about here. Describe the effect. Use specific terminology. This is constructive interference. How's that going? Does that make sense to you? Okay. So, for whatever reason, when I made this sheet, I only put these instructions once. But what I'd like for you to do now is to take these instructions and follow those instructions for this wave, the set that's on the bottom. Okay? So go ahead and do the same thing. So you're going to determine the frequency first. Again, 2 seconds are shown. Then you're going to draw the resultant wave. And then tell me what kind of interference you have there. Okay? So I'm going to give you just a minute or 2 with your partner or partners, your table friends, to figure that one out. Go. All right. So, friends, you've looked at this one? Is the frequency of this one the same as the ones above?
No.
Higher frequency or lower frequency?
Higher.
Higher frequency. What is the frequency of that first wave? 6 hertz. Tell me about the second one. Oh, it's frozen. Oh no. Thank you. What about the bottom one? Same. All right. Now, that wouldn't be very interesting. I mean, like, it was at a different frequency. That's cool. The resultant wave in the blank space below, I figured out for this one, is it going to be the same thing? What's different about this situation? What did you say? It is destroyed. Why is it destroyed?
Because one is going up and the other one is
Okay, so if we look up here, we've got a crest to start that wave at the top, right? But at the same time that this wave is at a crest, this one is at a trough. And so if we add those together, I've got A1 here, and I've got A2 here. What's going to, that's supposed to be a 2. What's going to happen to those two? It's going to be done, right? At any other point, and you could line up, like you could take a ruler and go little bit by little bit by little bit. If you move it vertically across, move it horizontally while it's standing up vertically, I guess. Every single moment, they're going to destroy one another, aren't they? Yes. They're going to be destroyed. Yes, they are. I just like to say that over and over. So what is the wave going to look like? It's going to be flat. That's the easy one to draw. There you go. Boom. Okay. What is that called?
Flatline.
Flatline, that would be a non-technical physics term. I want to know the technical physics term that goes with it. Destructive. And this, I would call this completely destructive.
So destructive is just when it gets
Mm-hmm. Yeah, when it like decreases in amplitude.
Okay.
Yeah. All right. One more little thing that I want to write down on this side before we flip it over. Okay. I wanted to label these, and it makes more sense to label them once we've looked at them. So these two waves, these two sets of waves, look very similar, right? In both cases, you've got the same frequency that's at the same place at the same time. But this one, the fundamental difference between the two is that the top one, they both have crests at the same time, and they both have troughs at the same time, right? Whereas in this one, you've got a crest and a trough at opposite times. They keep flipping, flipping, flipping. So the top one is an example of when you have two waves that are in phase. And the reason that I introduced this term to you is that you may hear this in math as well when you're talking about sine and cosine curves, okay? Sine and cosine curves are out of phase. They're 90 degrees out of phase, excuse me. These ones are in phase. These two right here are completely out of phase. (180 degrees opposite). Okay. If you have two waves that are exactly opposite of one another, they're out of phase. And again, if they're lined up, they're in phase. Are we getting this thing? Is it making sense? Okay. So now this part's going to be a little tricky because on the back, I didn't put this either. I feel like maybe when I do it, I should copy and paste this a few times. I didn't. So you have to remember these three things. Determine the frequency of the wave, draw the resultant wave, and then we'll describe that together. I want you to flip it over to the back. There's one more for you to work on. Okay? So take a look at this one. Give it a shot, and then we'll discuss. That would be kind of a waste of our time. So what do you notice in this one? What is different? They do. The top one has a frequency of 5 hertz. And the bottom one has a frequency of, I just wrote it down without even asking you. Sorry, because I knew it was coming. What's the problem with this? Maybe not problem. What does the resultant wave look like? Any ideas? Or any places to start? What's going to happen at the beginning, at that very first line? We'll call that line number 1, 2, 3, 4, 5. What kind of interference are you going to have at line number 1? Destructive, right? So you have a point of 0. What about at 2? What about at line 2? Constructive or destructive interference?
Constructive.
Constructive interference, right? It's going to go really, really far down. like so far. What about at line 3? It's destructive again. Line 4, constructive, way far down again. And at line 5, destructive again. Okay. So you might be tempted to just connect those, which isn't quite right. But the game is that you can line this up, and at lots of different places, you're going to get versions of constructive and destructive interference. Now, I could task you to do this. I could put it on a nice grid paper so that you could do it. It'd just be kind of a pain in the rear, and a lot of time would be taken. I'm going to show you what it looks like. Okay. So here are the two waves. I copied and pasted from this example. I just took the numbers off so that you get to count, because counting is a fun skill to have, right? So you got your 5 hertz and your 6 hertz. And when you add them together, this is what you get. It's kind of weird, right? Megan, you look like you don't believe me. She's like, what? Like, really? 0? That's what we said there. 0. Or -0, like they're weird. But you get this thing where you get this right? And remember that the amplitude has to do with if this was a sound wave, it has to do with the pitch, or not the pitch, that was terrible. It has to do with the volume, right? Amplitude has to do with the volume. So you've got this thing where this wave happens, but the amplitude gets smaller and bigger and smaller and bigger, which means that it gets louder and softer and louder and softer. Okay. When I show my students this, they're like, okay, that's great. Whatever, I don't believe you. I mean, maybe, like, I can see that it happens, but let me show you that it happens. Let me give you another opportunity to do it. You've seen this one, right? We used this last week or 2 weeks ago or whenever that was. Do you remember how frequently this thing vibrates when I strike it? 256 hertz, right? 256 cycles every second. Wah, wah, wah. You remember that? Like, it just keeps going and going and going. So now I've got that. I'll do it again in just a second. But I also want to introduce you to another tuning fork. Okay? This one's it's actually the same tuning fork. Cool. Right? This one says 256 as well. So that means that this one cycles at 256 cycles a second, but it looks a little bit funny because it's got these weights on it, right? So just like with my pendulum that would cycle at the proper period with just a certain length, this does the same thing, but now I'm adding mass at different places. And can you imagine if I took that pendulum and instead of just having that bob at the end, if I put another mass in the middle, can you imagine that it might do some funky things? It might vibrate at a different frequency. So this vibrates at a little bit of a different frequency. So I'll play this. If you're musically inclined, you might notice a difference. Or if you're not musically inclined, you're like, that sounds about the same. Like it's pretty darn close. Hey, can you go close the door for me? Just because those loud children are loud. All right, so now I'm going to play them both at the same time. So this one is at 256. This one is just a little bit not 256. Okay, might be a little high, a little low. I'm not going to worry about which one it is. I just want you to listen to these. So here we go. Do you hear that? That's this. That's those two waves that are both traveling to your ears. One's at 256, one is at 258 or something like that, right? It's just a little bit off. And the just a little bit off causes that wah, 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 wah. If you are in a musical ensemble where you play an instrument, this is exactly why you tune. Okay. If you've ever listened to like a, 5th grade or 6th grade band, when you've got like, I'm thinking like the trumpets, right? Like they're not quite in tune. And so if they all play a note, like they all play middle C, but some of them aren't quite in tune, then you get this exact thing. It's not pretty. Like it does not make the music that we expect. Okay. This thing right here is what we call beats. Okay. Beats. Wah, 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 wah. You'll hear me doing that a lot for the rest of the day today. So those are the beats. That is the result of two wave sources with similar but not identical frequencies. Okay? When those two wave sources with similar but not identical frequencies interact, okay, the interference causes both constructive and destructive, or I'm going to say interaction, sorry. Causes both constructive and destructive interference. Okay, alternating. When you have constructive interference, you're going to get big amplitude. Big amplitude is when it gets loud. And when you get destructive interference, the amplitude goes down, and then it is faint. It is absolutely possible to measure the beat frequency or the frequency between the two wave sources. Perhaps the easiest equation that you're going to learn from me all year. You ready for it? Here it comes. F sub B, so this is the beat frequency, is equal to, it's a little bit funky because it has an absolute value, but friends, absolute values are nothing to be afraid of. F1 minus F2. That's it. That's it. The beat frequency is just the difference between the two frequencies. Okay. So the beat frequency of the example that we had would be 6 minus 5. 6 minus 5 is 1. And it gets loud once every second. Questions right now? All right. Send somebody else, not the same person, unless you really want to, up to get a blue sheet, one per person. All right, so I'm gonna give you a chance to do this, to see how this works today. Okay, so you are going to get a tuning fork. All of the tuning forks are back here. They're put on a piece of paper because tuning forks are manufactured to oscillate at specific frequencies, right? That's what I was telling you before. Okay, these tuning forks do not have big resonance chambers so that they're not super loud, so you get just one at a time. Okay, so you're gonna hold it very tight. You are only going to use a mallet to strike it. When you strike it, you might not be able to hear it if you're far away, but if you put it up next to somebody's ear, can you hear it? For sure you can hear it, right? It's pretty loud, okay? So you want to strike it just with the rubber part of the mallet, okay? When you are done with it, you can bring it back. If you would like to take a couple of them at a time, that's absolutely fine. I would ask that you take a little piece of folded up paper to set on your table so that they don't clank on the lab tables. Does that make sense? Okay, we're trying to protect them so that they can be used for many, many years to come. If you accidentally hit it with something else, dampen it right away, and please, please be careful. I should not be able to hear all your tuning forks while you're taking this data. Okay? We are going to use microphones with our computers so that we can take some data, so you're actually going to be able to see this on the Chromebook using Logger Pro, or excuse me, not Logger Pro, graphical analysis, okay? When you strike your tuning fork and then hit the collect button, you should be able to see a nice sine curve like this, the up and down curve. If your data comes out really icky the first time, then just take it again, right? It's all good, okay? You're going to repeat a couple of times. Notice how the wave changes and the loudness differs. And then you're going to find data points. And if you need help finding figuring out how to do that, let me know and I'm super happy to help you. You may want to highlight or underline this so that you know it and you don't forget. You're going to complete 3 trials for each of 2 tuning forks. You're going to make a data table on what does it say there, friends? Separate sheet of paper. Yes, please. Separate sheet of paper and record your data. So you're going to measure the period of the tuning fork. Oh, what is period? Do we remember? Time for what?
One complete cycle something.
Mm-hmm.
The time it takes for...
So time from crest to crest or trough to trough. Yep. Okay. So you're going to determine the period of the tuning fork. You're going to measure the tuning forks 3 times, find the average, and then find the frequency related to that tuning fork. Okay. Compare the measured frequency with the one that's stamped on there and calculate your percent error. If you're not sure how to do that, you look at the back and the percent error equation is right there for you. Okay? Once you finish that, and that should not take a super long time, then you're going to move on to the beats part. This is the more exciting part. When you do the beats, one of you gets to turn into, I would describe it as like a Wolverine or Edward Scissorhands. I don't know if you guys even remember that movie. That's like a super old movie. Remember that? It's good. It's a good movie.
It is a good movie.
Yeah, it's like, reaching way back. Yeah, like when you're little, for sure. Yeah. Anyway, so you're going to take 2 tuning forks because for beats, you need 2 frequencies, right? You're going to subtract them. So my recommendation, please listen to this because otherwise you're going to get frustrated. Okay? I've been doing this for a lot of years, and this is the way that I've figured out works the best. You're going to choose 2 tuning forks that are vibrating at the same time. I would suggest that when you choose them, you choose tuning forks that have very similar but not exactly the same tuning forks. So don't get one from this end and one from this end of the paper because they're, divided by note. So pick 2 notes that are very close. I would recommend putting one in here between your first and middle fingers and then one in here between your other 2 fingers. So you hold them like this so you look a little bit, you know what I'm saying? And then go like that. And then you're going to put the microphone right here in between so that it can get data from both of them. Okay? And then you're actually going to be able to see, hopefully, again, this might take a couple of times, you hopefully will get to see something very similar to this. Okay? And from that, then you can calculate the beats. All right? You can work in groups of 2 or 3 if you guys just want to work at your tables. That's totally fine. The vernier equipment is over there. The tuning forks and mallets are over there. Go, go, go.